Hello and welcome to Group 15's Assignment 3 presentation video for KIB2003 Mechanics of Materials. This Group 15 consists of Afif, Haziq, Daryl, Hazrat and Faris. The title of our presentation is the Deadlift. In this presentation, we will go over the introduction, methodology, the learning outcomes and also the conclusion. On to the introduction. Now, biomedical engineering is a wild field or a very big topic. It spans into tissue engineering, medical devices, sports biomechanics, and many more. As a group, we decided to explore into sports biomechanics along with mechanics of materials. In this experiment, in this presentation also, we will aim to achieve 3 learning outcomes. First one is to solve problems involving body under action of axial or torsional load. In LO2, we solve problems involving stress in beams. And in LO3, we evaluate stress and deformation to a compound load. Now on to the deadlift. We chose to analyze the deadlift. According to the Collins English Dictionary, the deadlift is a type of lift where the weight or the barbell is lifted off the ground until the lifter is standing up straight. As you can see here is our video where we took pictures of each different parts of the deadlift when our subject was carrying it out. As you can see, the barbell starts on the ground, onto the shin, and until the subject has lifted it up, and onto the methodology.
Thank you. Now I'll proceed with the methodology. The experiment was conducted in the gym. Firstly, the length of the bar and the weight plates or loads were taken to determine the dimension for calculation purpose. Next, a total weight of 1100 Newton of barbell were prepared for the experiment to be lifted by a subject. Then, one subject performed a conventional deadlift once on the barbell correctly. The actions were filmed and snapped with camera to observe the bending on the bar. Next, the subject performed sumo deadlift on the 1100 Newton barbell once again, and the actions were filmed and snapped with camera to observe the bending on the bar. The sumo deadlift was repeated with total weight of loads of 1000 Newton and 900 Newton, and all data were taken and tabulated. The data obtained were used to calculate the shear stress, bending moment, moment of inertia, and the maximum bending stress, and the shear force and bending moment acting on the bar were drawn in diagrams. So here are the deadlift methods that were performed during the experiment. So this is the conventional deadlift method. And this is the sumo deadlift method. Not the difference in the positions of the subject's hand between both deadlift methods. Throughout the experiment, we have maintained 3 precautions to ensure the accuracy of data and the safety of the subject during deadlifting the barbell. Firstly, the subject must be healthy and strong enough to deadlift a 1100 Newton barbell to avoid unwanted accident from happening. Next, the plates have to be in the right positions on the bar to ensure balance with the subject and the barbell. Lastly, the eye should be at the same level with the ruler measurement to avoid parallax error. Now, I will hand the presentation to the next presenter to discuss about the results and the discussion. Thank you.
Hello and Assalamualaikum. My name is Afif. Let's move to the third content of our video, which is the learning outcomes. There will be 3 learning outcomes that we will discuss in this video. and we will show the calculation and discussion of the result. The first LO, the LO1, is solving problems involving a body under action of axial and torsional load. So first of all, we draw a free body diagram, and we have set specific points on the barbell, which we have the P and Q are the points at both ends of the bar, and R, S are the point of the subject's grip. All forces that exerted are shown as in the diagram. Next, this one is the cross-sectional free body diagram at both ends of the bar, which the force direction is exerted downward, and the radius of the bell is measured, which equals to 1 centimeter. So for axial loading, we can calculate the shear stress in the bar. So the formula for shear stress is F divided by A. F is the force exerted and the A is the area of the cross-sectional area. So the force is 550 Newton and the area is pi times with 1 centimeter squared. And we got the shear stress is 1.750704 megapascal. So this value is quite high because the force exerted on the area is quite high and the area is quite small. So the shear stress resulted is high. Then for the torsional loading, we can calculate the maximum allowable torque for this system. Given that the maximum shear stress tau max equals to 537 megapascal, and the polar moment of inertia J, the formula is equals to pi r power of 4 divided by 2. The r is the radius of the cross-sectional area, and we got that the J equals to 1.5708 times with 10 power of negative 8 meter power of 4. So from the tau max and the J polar moment of inertia, we can calculate the maximum allowable torque. T equals to tau max times with J divided by C. C is also the radius. We include all the data that we have calculated and we get the maximum allowable torque T equals to 843.5196 Newton meter. So that's all for LO1. Let's continue to the second LO, the LO2, which is to solve problems involving stress in beam. For this second LO, firstly, we will calculate the maximum bending stress. The formula for maximum bending stress equals to MC over I. The M is the moment, C is the radius, and I is the moment of inertia. We have the value of the C, but we don't know the M and I. So let's calculate for the M and I. So for the moment, the M, we will look at the point P to R, and also we will look for the point S to Q. So from this, the moment formula is Fr. F is the force and R is the distance. So we get the moment equals to 335.5 Newton meter. Next, for the I, the moment of inertia, the formula given for a circle is 1 over 4 times with pi r power of 4. And then we insert the value of r. And we get the value of I is 7.85 times with 10 power of negative 9 meter power of 4. So we have got the data for all parameters for the C, M, and I. So we include in the maximum bending stress formula, and we got the maximum bending stress is equals to 0.427 megapascal. This value means that the maximum bending stress that the bar can handle at that point is 0.4271719 megapascal. So if it exceeds this value, the bar will start to bend and deform permanently. Next, I will pass to Hazrat to continue the discussion for the shear stress and bending moment diagram.
Hello everyone, my name is Hazrat Khalis and I'm going to show you the shear stress and the bending moment in a graph. Before we dive into the graph, we need to know how we calculate the shear stress and the bending moment, which we use the third Newton's law. The third Newton's law, or the action-reaction force, is defined as when the action force has a reaction with the same magnitude but different direction. In our case, which is the barbell, it is a downward reaction and upward reaction. The third Newton's law also states that all parameters will be in an equilibrium state. The body will be in an equilibrium state. So, if we calculate the shear stress and the bending moment, the summation will be 0, which is the summation F becomes 0, summation M becomes 0. After that, we will see that the barbell have 4 distinguished points, which are P, R, S, Q. All these points indicate the reaction of the shear stress and the bending moment occur. So, it will be subdivided into 6 sections, which is V1 until V6, M1 until M6. As you can see, all the V and M is at the downward reaction and the anti-clockwise respectively. So there are 6 sections. So we could use the formula from the previous slide, which is the third Newton's law, to calculate each of the section parameters. So we will get this. For the shear stress, as you just previously see, it is a summation F. After that, it will be divided by the area of the barbell to get the shear stress. So, for the V and M, this is the result from the section 1 until 6. From this result, we could plot the graph. So, now start with shear stress diagram. It is said that the shear stress diagram is from V1 until V2, it is negative 0.175, but at V3 and V4 it's 0, and at the V5 and V6 it is 0.75. Why are they positive and negative 0.75? This is because you need to remember we're using the third Newton law, which indicates the equilibrium state. So when we summation all of the forces, it will become 0, which follow the rules. And why is there a 0 in the graph? Well, the V3 and V4 is where the gripping force is being held. The gripping, there is no shear stress occur in the gripping. So let's move on to the bending moment. As you can see, there is only 4 points, but there is a 6 point there, which the M2 and M3 and the M5 and M4 is distinguished as 4 different dots, because the distance between the M3 and M2 and M4 and M5 of those two is so small that in the graph plotting it is near to become a singular dot, but we must distinguish as 2. So we can see that M2, M3, M4 and M5, at that point the moment of the bending moment is negative 335.5, whereby the M1 point and the M6 point is 0. This happened because when the bending moment occurs, it occurs at the gripping force because the tension is needed to uplift the weight of the barbell that include both ends of it with the flat weight. This will aid the subject to increase its output to lift the barbell. But in the end, the barbell will bend nonetheless because of the weight from each end. So that is all for LO2. Thank you. Now we will move on to LO3 presented by Faris.
Assalamualaikum and hi. My name is Muhammad Faris bin Muhammad. Now we will move to LO3, Learning Outcome 3, Stress and Deformation to Compound Load. In this part, we will calculate the maximum allowable stress. Here, the formula of maximum allowable stress. The formula are the maximum allowable stress equal to yield stress divided by factor of safety. In this experiment, the yield stress of the bar is 415 megapascal. The factor of safety is 6 because the bar is able to support 2 loads with the with equal weights. From the value that we obtained before, we use the value and put the value inside the formula. 415 megapascal divided by 6 and we get 69.167 megapascal. This is the value of maximum allowable stress. Next, we will calculate the deflection of the beam. There's two equations that we need to calculate the deflection. First, the formula is delta, the deflection of beam, equal to strain times the length of the bar. And the second equation is the strain equal to stress divided by the Young's modulus of the bar. And we simplify the equation and we get deflection of the beam equal to stress times with the length of the bar divided by Young's modulus of the bar. For the bar, the Young's modulus value is 205 gigapascal, and we enter the value inside the formula. 1.75070 megapascals times with 2.13 meters divided by 205 gigapascals, and we get 1.819 times 10 to the power of negative 5. And we simplify the results and we get 18.19 micrometer.
In conclusion, as a group, we were able to achieve the objectives, which were the 3 LOs. First, in the analysis of the barbell under axial and torsional load, it was concluded that the bar experienced a shear stress of 1.75 megapascals while under a load of 1,100 newtons. It is also seen that the maximum moment of the barbell was at 843.2 Newton meters. Second, the stress with the barbell at different sections were analyzed and plotted in a graph. It was observed that the yield stress, which is the stress under the bar which can uphold before the plastic deformation occurs, was approximately 69.167 megapascals. It was also concluded that the shear stress acting on the bar at different points, which was V1 and V2 and V5 and V6, was negative 0.175 megapascals and 0.175 megapascals respectively. Third, the deflection that occurred in the barbell was calculated to be at 18.9 micrometers from the Young's modulus of the bar, which was 205 gigapascals. That is all from us. Thank you so much.